All right, so welcome back. So based on the backdrop I have given, we would apply these concepts of minimization and maximization in the extreme value theorem, or let's say the relative extrema, and then get to see how we apply what the necessary condition is and what the sufficiency condition is. All right, so let's get into it with the basic introduction I've given. All right, so let's first understand the concept of a relative extrema, what a relative extrema is and what it's not. Now, looking at the graph we have on the screen, okay? Now, it says that suppose that a function is said to be increasing on an interval I, then the assumption is that for any two numbers x1, let's say x2, in I, then x1 is less than x2. Okay, so think about this from this perspective. Okay, so if we are on this is called this is a polynomial. Okay, and we are on this continuum. Let's pick 2 points. Let's say x1 and x2. So this here, x1, the distance or the interval x1, x2 is what we are calling I. Okay, now if we pick these 2 points, x1 and x2, and it turns out that the value of x1 is less than x2, then on that interval I, we would say that x1 or the function is increasing along that interval. Okay, so I think this is very obvious, okay, that we can all see it. Now, if we did the reverse of it, where if probably we choose again an interval, let's say x1, x2 again, and then if x1, okay, if let's say x1 now is less than x2, then x1, function of x1 should be is greater than function of x2 in that case. Then in that case, we would assume that we are decreasing that interval. Now, this thing it looks so very obvious at the moment. So because it's a graph, it's a graphical representation of it. So you can easily see at what point we are increasing and at what point we are decreasing. For instance, so it's easy to say that along the continuum or along the interval, let's even say from x1 all the way to b, or even from A all the way to B, you can easily see that the interval there is increasing, and it probably we also took the interval from B to, let's say, C. Here we can also see that on that interval we actually experiencing a decrease. However, it's not always the case when it comes to these instances. You may not always have the graph to show at what point we are experiencing the increase and at what point we are experiencing the decrease. Oftentimes, you're only going to be given the polynomial, and probably you have something, say f of x is x squared plus maybe 4x. Okay, and this here probably represents this polynomial. Or probably says s cubed plus 1 over 3x. Okay, so probably this represents just a certain polynomial, and on this you can tell where we are increasing or where we are decreasing. Okay, so that's what we would be interested in. So we are interested in supposing we are increasing, at what point are we at the highest, or at what point is the highest? And if we are decreasing, at what point are we at the lowest? That is the idea of this relative extrema. Okay, so extreme, which is the relative extreme point. So supposing we have this interval I, and on I, along that interval I, we are increasing. At what point is the highest possible point, and at what point is the lowest possible point? Now, think about it. Let's bring it into the real business sense and try and understand this. In the case of let's say a business, An organization.
Your class is face to face.
All right, thank you for muting the presentation. All right. Now, so for instance, if you were producing a certain number of outputs, okay. Now, you have a certain range within which you can produce certain outputs. At what point are we producing the highest range of outputs that gives us the highest possible revenue? That's the idea of this thing that we are putting across. Also, for instance, if we can reduce our prices or a certain range of values, at what point are we reducing our prices maybe to the lowest possible point that we would not be incurring losses? Now, these are very practical applications of these concepts in real business sense that we need these concepts to help us understand. Okay, so that's the reason, or the idea, the reason why we actually try to apply this concept of relative extrema and relative. Yeah, so we'll see what the extrema, or the global maxima, and then the minima and stuff are. Okay, so if we take it into the case of differentiation, okay, it says that, okay, so another approach to determine whether a curve is increasing or decreasing within an interval is to apply differentiation, which is quite a simple procedure. And it's based on the following rule, okay? So now, if we are to apply differentiation on this concept, then if we have a function f, okay, let's say function f, and f is differentiable, okay, on the interval AB, okay. If f of x, or if f prime of x is greater than 0 for all x in AB, then f is increasing on AB. Okay, so if we have all the range of values, okay, on an interval, let's say we have an interval and we take the derivative, the first derivative of our function, and then if you substitute all the values of on that interval into your derivative, and all the functions, all the values, they actually do get a value which is greater than 0 for all what's it called, x, for all x values along that interval. So then we say we are increasing on AB. So let's say we have a certain let's say we have something like this. Can you help us mute the fellow? All right, so let's say we have a certain so we have this function here, okay, and we start from here. Let's see points. So these are, let's say, this is our x-axis. So this is 0, this is 1, probably this is 2, this is 3, this is 4. And let's say that the function is probably sometimes the x cubed. Okay, this polynomial is x cubed. If you take the derivative, let's say, and you have, let's say, 3x squared, okay, equals 0. Now, if you take each value of, so we take 1, substitute it here, okay, and you find the value. Now, you substitute 1 into the value. So let's have, this is just a fictitious example anyway. Okay, so we put 1 into this, and you're going to have something. This is going to be 3. You put 2 into this, okay, and this is 4. 4 times this is 12. You put this into this is 9. 9 times 3 is, I think, 27. You know, in that order. You put all these, and you notice that all these are greater than 0. So all we're saying is that, so if you take that interval and you take f prime of x, and f prime of x is greater than 0 for all x in AB, and this is the interval AB here, this interval is AB, then we can say that then the function is increasing on AB. The reverse applies when we take f prime of x, and for all the values of x, okay, f is decreasing. Then we'll see that if all the values of x are less than 0, maybe you're getting negative values or something. Then at that point, we would say that the function is decreasing in that interval. Any questions so far? All right, so we give an example as this. So we given that we have a certain function, 8x minus 2 over 3x cubed. Okay, it says determine whether the function is increasing or decreasing within the intervals minus 2, 1 and 4, 7 on the axis here. Okay, so the graph of the function is shown as this. So you're lucky here, we get to see the graphical representation of this function. So this function here, okay, is the same as this graph that you find here, okay? So we are interested in looking for the interval minus 2 and 1. Okay, so suppose that we are to get all the stuff here. So maybe minus 2, this is 1, this may be minus 2, depends, or probably 1 is here and minus 2. Okay, so this is minus 3. So let's say minus 2 is somewhere here. Okay, so once we take the derivative, we're going to just check out whether this is increasing or decreasing. However, we can see it. You can just eyeball this and then you can see whether it's increasing or decreasing because the graph is, it's obvious, pretty obvious, yeah. All right, so we take the derivative, which is f prime of x, and I'm pretty sure everyone at this moment, everyone can take this, can do this and take this derivative here. Okay, so if you bring the 3 here, to multiply by 3 over 2, you're going to get this 3 will cancel and you're going to have 2x squared, okay? And the 18 becomes 18x becomes 18. All right, so you have this expression here. Okay, so now if we have our first derivative as this, so we have taken the derivative of the function and we have 18 minus 2x squared. Okay, now we want to evaluate it along the points, that interval, minus 2 and 1. So first we substitute minus 2 into this expression and we have 10. Okay, and then we substitute positive 1 into the expression and we have 16. Now both 10 and 16 are greater than 0, and so along the interval minus 2 and 1, okay, sorry, minus 2 and 1, we can comfortably see that the curve is increasing along that line. Let's go back to the graph and see it. So if we have, let's say, minus 2 here, and probably we have, let's say, 1 here. So let's see, 1, and this is 2, and probably this is 3. So if we're moving from somewhere here, all the way to 1, minus 2 all the way to 1, you can easily see that here the graph is increasing. Okay, it's increasing, and that's the same thing happen. Now let's look at the case of 4 and 7. 4 and 7. So again, we apply the same notion, the same idea. And so when x equals 4, we substitute it into this expression, and we have minus 14 when x is 4, and when x is 7, we have minus 80. Now, so for minus 14 and minus 80, both are less than 0. Okay, so on the interval 4 and 7, we can say that our curve, okay, our function is falling, our function is reducing, okay, in that regard. Now, if we again come here, so let's say if we have something, say 4 here, and probably we have, let's say, 7 somewhere here, and 4 here, it looks pretty obvious again that on the interval 4 and 7, the curve is reducing. All right, Bright, you have your hand raised. It's a question, please go ahead. Hello, Bright. Okay, when Bright is ready, he would ask his question. Okay. All right, so guys, any questions so far? This is very it's quite straightforward concept. All right, Aqua Bernard, you have your hand raised. Please go ahead and ask your question.
Please, I just got confused. Can you just go over one more?
What exactly did you get confused about?
Reducing aspect.
So were you following from the beginning? Tell me, how did we start? The whole thing? What are the steps, and how do we notice that this is reducing and stuff?
But you're also comparing to the graph format. That's why I got confused.
Yeah, so I'm just asking you, how did we start? What? Just tell me from the beginning so that I can know exactly where you were paying attention and then where you lost your attention. So we started. So for instance, this is the function. What do we do to this function?
You've been asked to determine whether the function is either increasing or decreasing with the negative 2, 1, and 4, 7. That's on the x-axis. This someone is also
all right, so we have this function here, and you've been asked to determine whether the function is increasing or decreasing along the x-axis. So the first thing we do is to first take the derivative of the function. And when you take the derivative of the function, you now test given the points or the coordinates or the intervals, okay, the extreme values of the intervals to see whether along that interval is the function increasing or decreasing. Okay, so probably in that range, for instance, someone says that so if you're selling a bottle of water and maybe for 2 cedis, or we can sell our bottle of water between 1 cedi 20 pesos and 2 cedis. Now, if you were to sell it any price between 1 cedi 20 pesos and 2 cedis, chances are that our revenue would be increasing, or demand will still be increasing along that line. If you're selling it anything between 4 cedis and 7 cedis, chances are that maybe demand could be falling, or yes, our revenue could be falling. So we want to test whether at what point would we be experiencing an increasing return. So sorry, not returns necessarily, an increasing function. Okay, and at what point would probably be decreased. So the first thing we do is, given the function, we take the derivative of this function. And so 18x minus 2x, 2 over 3x cubed is the derivative of it. So we can say f prime of x is 18, okay, minus 2x squared. So this is the derivative of this function here. Now, we have been given the two extremes of the interval, so the relative extreme points of the interval. So we have minus 2 and 1. So this is the interval we want to test. So you substitute the extreme values, the two relative points of the interval. So we have, let's say, an interval. If we come here, I am interested in minus 2. So this is, let's say this is 1 and this is minus 2. So let's say this is minus 2 and probably this is 1. Okay, so we are interested in this interval. Okay, we're interested in this interval. So I substitute the values of these extreme points, okay, the 1 and then minus 2 into this expression. And once you have done that, if what you get tends to be greater than 0, okay, for all the values. So for all values in between, what's it called, the minus 2 and 1. Okay, if all the values between minus 2 and 1 actually are giving you something greater than 0, then we can easily tell whether we are increasing at that point. Okay, and if all the values are not, then you know you're not increasing at that point. So, but the smartest thing to do is, these are the two extreme values. These are the two ends of the interval. -2 and 1. So if the two ends both give you something greater than 0, then there's no point in testing the values in between. However, if probably -2 actually gives us something greater than 0, and then maybe 1 ends up giving us something less than 0, then probably you would want to shift it, come back, maybe try -2 and 0, or maybe -2 and -1, something, just to be sure at what point we are increasing and at what point we will not be increasing. All right, so this is what we did here. So having taken the derivative, we try the 2 points. So first, when x equals -2, when x equals -2 and you substitute -2 into this expression here, we had 10, positive 10, which is greater than 0. And then again, we take the next one, 1, when x equals positive 1. Okay, so when we substitute this into the expression and we have 16, which is also again greater than 0. So in both instances, when x is -2 and x is also 1, we have values that are greater than 0. So then in that case, we're saying that here along this interval, the interval -2 and 1, we would be experiencing an increase, or the function is increasing along that interval. However, the reverse fashion, we said we're supposed to evaluate 4 and 7. Okay, so we again substitute the values. So we are looking at this interval 4 and 7. We substitute the values 4 into the expression, then you have a -14. Then you also substitute the value 7 into the expression again, and we have -80. Now, both instances tend to be less than 0. Okay, so on this interval here, 4 and 7, because both are less than 0, we can conclude that we are experiencing a decrease on this interval. Bright, I hope you do understand what we're saying. Hello. Hello. Okay, so well, I hope, right, I hope you do get what we are putting across. All right.
Yes.
Okay. I'm sure it does. All right. Okay. So we can easily tell that now. Let's understand. Today's class will not have too many mathematical concepts. It will form the basis for what we'll do going forward. So, but let's see the other one: relative maxima and relative minima. Okay. Let's try and understand these concepts again, and then we'll apply them again somewhere. Now, so having understood what an interval is, and also understanding where we are either experiencing a decrease or whether we are experiencing an increase, the next thing we want to understand is now, on a particular interval or along an interval, which value is the highest possible value on that interval, and which value is the lowest possible value on a certain interval, or is along a certain interval. Now, the idea here is, there again, if we, guys, could you please mute fellow? All right, okay.
Hello, sir.
All right, so we've been able to mute the person. All right, thank you.
Hello.
Yes, you have a question.
Sir, please no. I'm sorry to interrupt, but other people want to join, but the group is full. The class is full.
Okay, all right, then
Four.
why are other people trying to join? Group 4 meets on Monday, isn't it?
Yes, sir.
So why are other people trying to join?
Hello. The group is full, but like there are more people to join the class.
But group 4 do not have, on the list, group 4 do not have more than 300 people. So how can we have more than 300? Last week, was it the same issue? Yeah.
Sir, please,
So
other groups have joined. Other groups have joined our class.
why are they
And really, they are
joining
saying
now?
that
Why are they joining
because
the class?
there we have no idea. We have to
Yeah.
leave
So
because our colleagues are in the waiting room.
yeah. So forgive me. I really would want to have all these problems solved, but how do I don't know why they're joining our class. I haven't asked them to join our class. I know lots of things are happening. The timetables are changing and you guys are having it a hard time, toggling between the classes and everything though. But well, maybe you could encourage them. We'll try and make another time for their group as well. Okay,
Sir, I think it's a wrong information given to them. Maybe the link was mistakenly shared into their group. That is group 2.
it's fine. You shouldn't worry about it. We'll find a way of figuring it out. Okay, I know things are
Okay,
quite
sir.
things are quite challenging. Yes.
I'm here, mommy. Yeah, please. On our timetable, group 2, we have business mass this morning.
Yeah, you have business mass this morning, right?
Yes.
And
group 1.
okay, so I just remember your course rep told me your timetable has changed, isn't it?
Yes.
Yes, it was.
Yes, please, I did that.
Yes, I remember. I just remember you just told me. Well, course rep, so you see the challenge. So what am I supposed to do? Like cut
Yes,
this group
please.
and teach the other group? It's not possible. Geez, this is just. Well, let's those who can join, let them join. Those who cannot join at the moment, let them hold on. We'll figure out something and have another class with them. Okay.
Okay, sir.
If there is no if they don't have what's it called besides even this group, they are doing their third session. You guys, it's your second session, so there's still going to be a challenge. So how about just after this one we have what's it called, our class.
Okay, I think that's fair.
Yeah, so I mean from 9:30 to let's say 11 o'clock or something, then we have another class. Okay.
So can we leave, sir, group 2?
Yes, I mean only those in group 2. Only those in group 2.
Sir, please, some of us, we have an alcohol writing class right after here.
Just you find your way around it. I can. It's difficult to please everyone. Okay, so those who can come should come. If afterwards, there are other groups you can also join. All right. So relative maxima and relative minima. Let's try and understand. If you are in group 2 and you can still continue to be in this group, that's no problem. Please continue to be in the group and have the class with us. But afterwards, I would just after this class, I will still have a class with group 2 again, so we can have okay, so we can see what happens for this one. Or probably I pay for the university. I don't know what's happening. I think everyone has a problem anyway in the University of Ghana. So, well, but the university no longer pays for cloud storage and all these professional courtesies. So we are limited to this one. So probably we just have to buy my own professional service so that you guys we can have as many as possible. Okay. So, but for now, my friends in group 2, please do not be angry. If you want to leave, fine, that's okay. If you still want to continue to be here, just be here and enjoy the class. But after this one, I'll have your class with you, okay? However, if you miss it for academic something class, there are other groups as well. There's a group on Tuesday. There are 2 groups meeting on Tuesday. There's a group on Wednesday. There's another group on Thursday, okay? Just try and join any of them and then we can...
Hey.
Yes, please.
So can I ask them to leave because we the original group force, we are still in the waiting room.
Even if I ask them to leave and decide not to leave, what do you do? Yeah, so we can only appeal to them. But so this is a dilemma. You can't do anything about it. I'm surprised that those who fix the timetable have forgotten that there is group 4 that meets this same time, and you put another same class at the exact same time. I don't get it.
So, sir, if we leave, it will be
our classes.
No, if you leave, your class will be 9:30. Okay, not 10. Immediately after this one, we'll just start with that one as well. Okay. All right. So my friends in group 2, you can leave, please, so that our friends in group 4 do not get disenfranchised. Okay. Okay. All right. So I think the number is reducing drastically. They're leaving 279, 278, 76, and 5. All right. So you can, friends of group 4, you can ask your colleagues to join the class. Okay. All right. So group 4, kindly encourage, first rep of group 4, kindly encourage your friends to join us. Okay. A lot of them have left. The number has really reduced to 263. Okay. All right. So let's go ahead. Let's understand what the relative maxima and the relative minima, the concepts of maxima and minima. Now, this is only gotten from the point maximum and minimum. Okay, relative maxima and relative minima. Now, so let me put this in a certain practical sense for us. Now, so like I was saying, if we are making bottled water, or if we're making some, let's say we have a certain product, and we have an interval of prices at which we can sell our product. Now, if we actually choose a particular price to sell, or arrive or settle on a price to sell our product, now at what price, at that price, how sure are we that that is the price that we are going to make the highest possible revenue or not? Okay. Or if we are looking at cost and we are looking at minimization, then at a certain price, or at a certain maybe cost of production, maybe that will be the cost that would incur the lowest average cost, or the lowest cost of production. And so along a certain interval, within a certain interval, what is the maximum and what is the possible minimum? That's the idea. So for instance, if we have this graph we have here. Okay, so this is the entire interval is probably, let's say, from sorry guys. All right, so we have this interval from this point all the way to somewhere here. Okay. Now, this whole interval here can have several short intervals. Okay, now, in between these, we can find what we call an overall maximum point and an overall minimum point. And we can also have a relative maximum point and a relative minimum point. First, let's understand the relative minimum and maximums, and then we will look at the overall maximum. Okay, now, so let's say if we take an interval, if we take this graph here, all high points are potential candidates of a maximum point. Okay, now when you have a high point, at the highest peak, or at the peak of the curve, that point, the turning point, or the rate of change at that point is 0. This is oftentimes, this is proven in physics. If you take a ball and you throw the ball up into the sky, notice that it goes up, it defies gravity because it goes against gravity. It gets to a certain point in the air, it stops and changes direction. Now, the point at which it stops and changes direction in the air, at that point, the rate of change there is 0. Okay, so from that point to the ground, we call it a Mahalanobis distance. So in several instances as well, when we have a curve, so we have, let's say, our graph, our curve here, rising, attains a maximum here. And then it attains this maximum, and at this point, it changes direction. At the point where it changes direction, the rate of change there is 0. And it goes down, down here. So again, it comes to the lowest possible point. Then again, it changes direction again. So at every point where it attains either the maximum or the minimum, the rate of change there is, okay? Now, so at every point, at every point where the rate of change is 0, that point is a potential maximum point, or what's it called, a minimum point. So here, this is some point we can call a local maxima, and we'll call this point a local minima. Okay, now if you compare, now this is another local maxima, another point, but these are the two highest points on our curve, on our graph. But if we compare the two, this point, the second one, let me call this A and let me call this B. This point here is higher than A. Point B turns out to be higher than point A. And so at point B is also, or point B could be referred to as our global maxima. Global maxima in the sense that when we compare it to all the other maximum points on our graph, this is the highest possible point. So it's our global maxima. Okay, now where we have a point where we do not have a smooth change of, let's say, a smooth change of how do you call it, direction. So for instance, if you took a ball and you just you throw it in a certain direction, or you throw it in the direction of a wall, and it hits the wall and bounces or reflects in a certain direction. This is a typical example. In that instance, we do not have we can really measure the rate of change at that point, because the rate of change there, or the change in direction there, was caused by something, and so we can really have. So here, the rate of change does not exist here, at least in terms of differentiation literature. So yes, only points where we can have that thing rises, attains a maximum and changes direction. Then at the point where it's changing direction, the rate of change is 0. Okay, so we'll see how this actually applies in real life. So the highest and lowest points are called the relative extremum. Okay, i.e. the curve is locally maximum or minimum. So here, these are the relative extremum points, or what we call the relative extrema. So this is an extremum, an extrema. This is an extrema. This is also an extrema. These are all maximum points. Okay. All right. So let's again try and understand how we apply this relative extrema concept here. Now, at the local or relative minima or maxima, also called the relative extremum, f prime of x equals 0. It means that is the turning point. That's the point where, let's say, the movement has attained the maximum and is changing direction. Okay. Now, what we need to do, there are two things that we do to satisfy this condition to be sure whether indeed this is the maximum point or a minimum point. Okay. Rule 2, which we call the necessary condition, is, however, we actually use the first derivative test to find the relative extrema. So when you have a certain function, you're given a certain function, x squared, let's say 4x squared minus 3 x, okay? So y equals 4x something. Now, the rate of change, the point at which when this function changes direction and gives and is equal to 0, at that point, we believe it's a maximum point or minimum point depending on what we will test. So if I take the first derivative of this, and let's say I have 8x minus 3 equals 0. At this point, it is a potential maximum point. Okay, this is a potential maximum point. But now, how do we know? But we need to establish that indeed, yes, that is the potential maximum point. Now, we have found the potential maximum point. If we go back, it is possible that there could be multiple maximum points on a curve. Now, if there are multiple maximum points on a curve, then we should be interested in the highest possible, or the maximum, the global maximum, okay? Not the local maximum, because think about it in real business sense that if I sell a product, let's say at 4 cedi 50 pesos, and I can make a profit of say of 1 million, and I can sell the product at 5 cedis and make a profit of 1.1 million, then it wouldn't make economic sense for me to still sell the product at 4.5, because it means there's something still there at 5 that I can sell and still make the same profit. So if you identify your maximum point, or your either your local, your relative minima or maxima, we must prove and be sure that yes, indeed, that point is actually or truly the highest possible point. And so we have what we call the sufficiency test, which is in layman's terms, we say is the second derivative test for the relative maxima. Now, suppose we take f prime of x, f prime of a, okay, equals 0. Then, to be sure that it's a maximum point, is actually the highest possible point or the lowest possible point, what we do is we take the second derivative. So you differentiate the function the second time. And when you take the second derivative of the function, let's do f prime prime of a, if f prime prime of a is less than 0, then the function is a relative maximum at a. If you take the f prime prime of a, or you take the second derivative of the function, and it is greater than 0, then the function has a relative minimum at a. Okay, so this f double prime of a, or the second derivative of the function, is what we call the second derivative of y at a. I know this is quite abstract, so let's get in some practical examples and then just see how it works out, okay? All right, so we take a function, say given the function 2x squared minus x to the 4th. A, it says find the points at which f of x is either minimum or maximum, okay? And okay. So all right.
The last check now. That person should not get person, you know.
All right, thank you. All right, so we have the function 2x squared minus x to the 4th. Find the points at which f of x is either maximum or minimum. And then indicate whether a relative extremum from question is a relative maximum or minimum. So we want to be sure. Now, at that point where we are saying is the maximum point or minimum point, is that the highest possible maximum point? So we take the first derivative. Now, if you take the first derivative of this function, 2x squared minus 4x to the 4th, we have 4x minus 4x cubed. Okay, and if you have this expression, we can how do you call it, do some factorization. Okay, here 4 and 4 common, so you take the 4 out, x minus x cubed. Okay, so if you have this expression again, we can again factor out 4 4x, then you can have 1 minus x, more like a quadratic, 1 minus x, 1 plus x in this sense. So you're having 3 different values. You have -1, +1, and in between -1 and +1, there's surely going to be 0. Okay, so that's like a range of values. So x could be at 0, x could be at 1, and x could be at -1. Now, these are 3 possible options. Or this is the interval. So you're looking at an interval -1 and 1. Okay. Now, so this is like the interval where potentially we can have our maximum value. Now, to be sure whether this is actually true, indeed, if it is true, then we would now take the second derivative of this function here, okay? Now, if we're taking the second derivative of this function, then this gives us the function 4 minus, if you take the derivative of this, you're going to have 12x squared. So we have the second derivative of this, okay, as this. Now, if we have this second derivative, let's test whether we are going to have our values either greater than 0 or less than 0, and see whether it's a maximum, which point is a maximum and which point will be a minimum. So first, when x equals 0, because we found 3 possible values of x, when x equals 0, then f prime of 0 would be 4 minus 0. Now, all this, if x is 0, we represent x to be 0 here. So it's like you're going to have something like 12 into bracket 0 squared, and everything here just dies off to be 0. So this is 4, and so this 4 here is greater than 0. Now, you remember the rule. The rule says that if f prime of a is greater than 0, then we have a minimum at a. If it is less than 0, then we have a maximum at a. So here we have a minimum. So when at point 0, we have a minimum, but at point 1, where we substitute the values of value 1 into this expression, this is going to be a -8. And -8 is less than 0, so we're going to have a maximum point. If we also substitute -1, -1 here, okay, so this is also going to be -8, because you're going to have -1 squared, okay, and -1 squared is 1, so 12 times 1 is 1. 4 minus 12 again will be -8. And you're going to, so at points 1 and -1, we have maximum points. And if we also have at point 0, we are going to have a minimum point. This graphically will probably look something weird like this, like the curve is going to look something like, it starts from a certain point, it comes down, then it goes up and up again, sort of. It will look something weird like this, where this point here, we would have something like 0. So probably this should even be touching the axis. So this is at 0, and probably, well, let me get it right. So they're both mixed. So you have both maximum, minimum, and probably maximum. So here, so let's say if I have this, no, this should be this. It should be something like this. Please forgive me. This will probably be -1. This probably would be 0, and this would be 1. Okay, it will look something. So graphically, it will look something like this: -1, 1, 0. Okay, in that order. Let's take another example here. This would drum it home the more, because this is more price and quantity. All right, Kinsley Asante, you have your hand raised. Please ask your question, Kinsley.
Sir, please, I would like you to go over how you had the 1 and the -1, the coordinates, the A. I didn't get it well. Yes, the A. For the B, I understand it.
Have you taken your mind back to, what's it called? Factorization, right? We go back to So you have this expression here, 4x minus 4x cubed. Okay.
Okay.
This looks, you can beat this down a little bit. Now, you notice 4. First, 4 is common to all of this. So another way of writing this is to take out the 4, and we have the x. Okay, you have this like this. Okay. However, this here, this expression here can further be broken down. We want to write it, we want to generate the coordinates for this. Now, you have something say 4x. Now, this here, when you factor this out again, this now is left with 1, isn't it?
Yeah.
Okay. Then you'll be left with x squared, okay, of this. Now, if you were to look for the factors of this, okay, so this is more something like a polynomial rule. When we are, it looks something like this. For a polynomial, you have 3 points across a polynomial. And if we can only have 3 points for a polynomial, it's always -1, 1, and 0. Okay, so it's like saying if you, I kind of like try to expand this point, this expression here. There are 3 possible values for this polynomial, and you have 1, -1, and in between. So it's like you're revolving around the how do you call it, the Cartesian plane, revolving around the x and y plane. So if I am at -1 and I am at 1, then surely in between -1 and 1, I have 0. That's more like it's a quadratic function. That's how come. Okay, and all quadratic functions have 3 points around the, how do you call it? What do you call it? The Cartesian plane. Yeah, so it's -1, 0, and 1. -1, 0, and 1. Okay.
Thank you.
So forgive me, I understand some of these things you guys, you may have forgotten because they are probably things that you have done way back in high school or something like that. But all right, so let's take a typical example. So suppose that we have a price P equals this, 18 minus Q over 4. Now we are interested in evaluating it along an interval 0 and 80, where Q is the number of products. So what is the highest possible output to produce or to give us the maximum revenue given this? Okay, so but we have, so we want at what value of Q will maximum revenue be attained. So now we have been given the price, okay, but we know if we are talking about revenue is price and quantity. Okay, so if we've been given an expression 80 minus Q of 4, okay, then we can multiply this by Q, sorry, not P. Okay, so that this gives us a revenue expression. Okay, so if you multiply this with Q, what we have is 80Q minus Q squared over 4. Okay, so this is our total revenue expression here. Okay, so now we want to find the maximum value. So we would have to take the first derivative of this. Okay, all right, so if you want to take the first derivative of this, one way you can write this function is, do you know you can write it as 1 over 4 80Q minus Q squared? Okay, so if you can take this expression as this or this form, life could be very easy for you. Then you can just differentiate whatever is inside here and just put it back into the expression. Okay, all right, so we can take this function here as this, and then once you've taken the derivative of it, you have 80 minus 2Q, then life goes away easily for you, and you just have to actually solve this. You don't have to work your way out in any sense again. Okay, all right, so we go ahead. Yes, Yes, David Ajoyi. David, please go ahead.
Sir.
Yes, please.
Yeah, sir, when I did the differentiation, I didn't get an 80 minus 2Q.
So what
Because
did you get?
when you differentiate the 1 in the bracket, you get 80 minus 2Q, all right, but you have to multiply with the 1 out of 4.
1 out of 4, and what do you get?
Yes. So I had 20 minus 1 out of 2Q.
20
minus 1 out of 2Q.
So you divide everything
by 4.
Okay, so
yeah.
You can, so here you can have 20Q minus 1 over 4Q squared, isn't it? And
yes, sir.
When you take this, you have 1 over 2Q squared and this. Okay. All right. So I think it will be a mistake. All right. Okay. So it's a mistake, I guess. I haven't really checked this.
Okay.
All right.
Thank you.
Yes. Thank you for drawing my attention to it. All right. So let's see. Let's do it together so we don't have to. All right. So we can respread this. ET 20Q. All right. So let's differentiate this. You can have, so here you have 20 minus 1 over 2Q, isn't it? Yes. So this is the expression. Okay. All right. That's fine. I'm not sure it would be a problem. It's not a problem per se because Q is still going to be 40, right? All right, so let's go ahead. So I think it's a typographical error. It's not a problem anyway. Okay, all right. So please, we have, for the sake of our friends who don't understand, okay, please, one way of rewriting this expression, again, like I said to you, is we can spread this because the 4 is dividing all the terms here. You can write it as 80Q over 4, okay, minus Q squared over 4, okay, all right. Then, which is like, you can have this 20Q, okay, and then if you take the derivative of this is like 2Q, okay, over 4. And then that is going to be, so 2 over 4, this goes to the use of 1, goes to this 2. So you have 1 over 2Q, okay? Please, are we okay? Equals 0. So this is the first derivative, R prime of Q, okay? Guys, please, are we okay? All right, so we have R prime of Q, which is this. So let's solve for Q. If we have R prime of Q, so please, this should be 1 over 2Q, isn't it? 21 over 2Q. Yeah. Okay, should be equal to 0. So if this is the case, then we can just do 20 equals 1 over 2Q. And so we solve for Q. So Q will be equal to 40. All right. All right. So we are assuming that Q at quantity 40, we would be making the highest possible revenue. So at quantity 40, we'll be making the highest possible revenue. But how sure are we? Because we are evaluating it between 0 and 80. Okay, and you're telling us that if we produce at 40, that's where we'll be making the highest possible revenue. How about output 50, 60, 70, and even 80 itself in this regard? So let's test to be sure that yes, indeed, this 40 is the maximum point. So what we do is to take the second derivative of our expression. So now we're going to do R prime prime of Q. Okay, if we do R prime prime of Q, we had 20 minus 1 over 2Q. Okay, now, so if we take the second derivative, or we differentiate the function again from the first derivative, this 20 goes away and this Q, so all we're going to have is negative 1 over 2. And negative 1 over 2 is less than 0. Now let's go back to what the rule says. The rule says that if we take the second derivative and it is less than 0, then we are at a maximum at point A. If we take the second derivative and it is greater than 0, then we are at a minimum. Okay, so we come here and we have taken the second derivative and we have a -1/2, which is less than 0. So indeed, we are at a maximum. This second condition here, this second derivative test, proves to us that yes, indeed, 40 would give us the highest possible revenue from our function. Okay, so we can substitute it into the original expression here to see what actual revenue that would be. So we go back. This is the revenue equation. This is the total revenue equation here. And we have found Q to be 40. So at what revenue would we, so it says that what is the maximum revenue? So at what revenue would we have? So this is 80 times 40 minus 40 squared all over 4. And when you solve this expression here, I think we had 400, and that's the same thing we have here. Okay. All right. This is there are more questions ahead that we're going to solve. So this is there any questions so far? So this is the trick. This is just the rule. When you're given the question, the first thing to do is take the first derivative. You take the first derivative, equate it to 0, and solve for the unknown variable, like we have done here. So we have the first derivative here. We equate it to 0, and then we solve for Q. Having solved for Q, the value we get there is the maximum value, okay? But it could be a maximum value or a minimum value depending on what the second derivative test will tell us. So if we are unsure, we conduct the second derivative test. And so you take the second derivative of the function. So this is the first derivative. So, okay, so let me write the correct one. So 20 minus 1 over 2q. This is the first derivative, which is r prime of q. Okay, so having taken this and solved for q, the next thing we do is take the derivative of this function again. So differentiate this function again. And in differentiating this function again, you have r prime of q. And then with the r prime of q, we had -1/2. And then you compare it to the test rule. If this is a negative value, or if it is a value that's less than 0, okay, we know it's a maximum. And if it is a value that is greater than 0, we know it is a minimum. All right. Okay, so Asari Regan, you have your hand raised. Could you please ask a question?
Sure. Please, the derivative we had, the 20 minus 1 over 2q. How are you able to get the 40? The 40 we had.
Okay, all right, okay. All right, so Mr. Sari, we said, so we said that at the first derivative, where you take the f prime of a certain function, let's say f prime of a, okay, it's equal to 0, isn't it? Because at that point, it go back, please mute your microphone, okay? All right, so first we said f prime of x, or f prime, or the first derivative of the function, at that point, it's equal to 0. And we proved it here on this graph, in the sense that at the point where probably the graph it rises, attains the maximum and changes direction, at that point, the rate of change is 0. If it were minimum as well, it reaches the minimum, and the rate of change there is 0. Okay, so please, do you understand that point there? So when we come and we take the derivative of our function, suppose we take f prime of q, and we had 20 minus 1 over 2q. Okay, this is f prime of q. At this point, this is the rate of change. This is the maximum point or the minimum point. So here we equate it to 0. Okay, so once we equate it to 0, we can easily solve for the unknown. This is what I was saying. So we are interested in finding the quantity that will give us the highest possible revenue. So here, this is like 20 equals this guy. When we flip this guy to the other side, 1 minus 1 over 2q. When we take it to the other side, it's like you add this same value to this side and subtract this value from this side, okay? Or you just add it to both sides and it goes away. So here we have positive 1 over 2q, okay? So you want to solve for q, isn't it? So this is like saying 20 divided by 1 over 2, okay, equals q, all right? So if you don't want to do it 20 over 0.5, which is 40, you can do it 20, okay, times 2 over 1, okay? And this is the same as 40, okay? All right, so Mr. Sari, please, do you get it now?
Yes, please. Thank you.
All right, okay, then, all right. Okay, so we had the quantity to be 40. So once we had 40, so our that quantity that gives us the possible highest revenue is 40, but we need to be sure if that is true. So let's be sure whether it's actually a maximum or a minimum. So here we take the second derivative of our function. So we take our 20 minus 1 over 2q, and we take the second derivative of it. And of q, sorry, r is supposed to be r prime of q. So we take the second derivative here, and this 20 goes away. You're left with minus 1 over 2. And because it is less than 0, we know it's a maximum point. Okay. All right. Okay, so let's progress. So we have seen the case of the maximum point and then the minimum point, the relative maximum and then the relative minimum, okay? Now, let's look at the last one, which is the extreme value theorem. Okay, very simple and straightforward something. Now, it says that, so we want to understand something. Now, if a function f is continuous on a closed interval, now please take note. Now here we are dealing with a closed interval. In the first instances, we didn't emphasize on the fact that we are interested in a closed interval, okay? Okay, so then the function has both the maximum value and the minimum value on that interval. So on a closed interval, mathematically we represented something like this, okay? And it says, note that one should guarantee that the function is continuous and the function is being analyzed in a closed interval. Now, the symbol AB in square brackets, okay? The symbol square brackets AB implies a closed interval, and it includes the endpoints A and B. Whereas when we have a normal bracket, AB, it implies an open interval and it excludes the endpoints AB. So what we are saying is, now, you do notice that, let me just take you back a little. Look at the question we solved. We were supposed to evaluate, we are supposed to produce, the lowest we can produce is 0, and then the highest we can produce is 80. But when we found our value, maximum value 40, we did not even consider the 0 and 80. It wasn't of interest to us. Well, because we actually were not interested in the endpoints, okay? And it wasn't a closed interval. So we are not really interested. Actually, it's an example of an interval that could be considered a closed interval, but the emphasis wasn't there. Or we are not to test the extreme values. That wasn't our emphasis. Okay, but now we are interested in a closed interval. Now, see, so it says the implication of the above definition is that the maximum or minimum points could occur at the endpoint since the interval is closed. Okay, so here, because we are looking at a closed interval, the fact that you probably have taken the first derivative and probably have identified a certain value as the maximum point, we still ought to check the extreme values or the boundary values. So for instance, we were given, let's say, let's supposing we have a closed interval 80, 0 and 80, okay? Now, although we found 40 as the maximum value, it is saying that sometimes it is possible that the highest possible value could occur, okay, at the extreme values, or could occur at the endpoints, which is either 0 or 80. So what extreme value theorem tells us is that, kind of in a market one sense, is that even though we have found the maximum point, okay, having taken the first derivative, done the first derivative test and the second derivative test, let's evaluate the endpoints, okay, the extreme points in addition to the maximum value, and be sure that indeed this is our maximum. This is our, so this, the understanding is this could be a local maximum at the same time a global maximum. However, there I don't have any example in mind, but there are instances where this could be a maximum, but actually the global maximum could be occurring maybe at the endpoints or something. That is if it's possible. So in that case, let's also evaluate the endpoints in addition to, right, so that we are absolutely sure there are no surprises at the end of the day. Okay, so the procedure to find the absolute extrema for a function f that is continuous on AB is, first, let's find the critical values of f, which means let's take the first derivative, equate it to 0, and solve for the quantity, or solve for whatever value there is, which is the maximum or the minimum value. Then evaluate the f of x at the endpoints AB and the critical values in AB. Then when we are done, the maximum value of f is the greatest values found in step 2, and the minimum value is the least value found in step 2. Okay, so I know this again, this is a little abstract. So let's take an example and solve it, and then we can all see what happens, okay? So let's again go this way. Let's solve our this question again, this time considering the case of the extreme value theorem. Okay, so extreme value theorem. So we have P equals 80 minus Q over 4, and we are evaluating it at within this closed interval 0 and 80. Okay, so quantity to produce is between 0 and 80. So we find our total revenue expression here. Okay, so this time around, there is an effort to correct it here. Okay, so here we have this expression as our total revenue expression. So this is total revenue. This here is total revenue. So let's take the first derivative of total revenue. So when we do dr dq, taking the first derivative, we have to equate it to 0. So dr dq should be equal to 0. So here we take the first derivative, which is 20 minus 1 over 2q, and that is equal to 0. Okay, so then if it's equal to 0, we solve for q, and then we find q to be 40. Okay, now let's do the second derivative test to be sure that that is the maximum point. Okay, now is it indeed a maximum point? So we take the second derivative, and we take the second derivative here, and we have minus 1 over 2, which is less than 0. So we can comfortably say that the quantity 40 is indeed a maximum point. Now, therefore, we are saying that therefore Q equals 40 is a relative maximum revenue value, a relative maximum revenue value. However, let's prove this with the extreme value theorem to be sure that indeed it is the absolute maximum value. Okay, so it says that, however, since the analysis is being carried over a closed interval, we need to verify the endpoints to be sure that Q equals 40 indeed yields the absolute maximum revenue. We don't want any instance where, yes, Q is a maximum value, but actually the highest possible revenue will not be attained at Q equals 40. So first, we will take the equation, we go back to our total revenue function. Our total revenue function we had was 20Q minus 1 over 4Q squared. Okay, this was what we had. Now, the interval, the closed interval was 80. And we found our critical value to be 40. Okay, so first we substitute 0 into the equation. So this is the first endpoint, 0. We substitute 0 into this whole equation, and all we have is 0, because 20 times 0 is 0, and all this times 0 would be 0. Okay, then we substitute the critical value, which is 40 here. We substitute 40 into it, and we have 400. And then we again substitute 80, which is the last endpoint into it. So when R equals 80, so we have this, and 20 times 80 minus 1 over 4, 80 squared.
Sir, please, we can't hear you.
All right, so we put it, we substitute this into the expression, and this also gives us 0. So both endpoints, having substituted them into the total revenue function, we found out that both would give us 0, this 0, and this 0. And the only one that gives us a high possible value, gives us any value, that is to write anything. All right, hello. Hello. All right, guys, please, can you hear me? I restarted my network, so I hope it's better. Hello, guys.
Yes.
Hi.
Hello.
It's better. Okay. All right.
Can hear you.
All right, sure. All right. Sorry, I noticed my network wasn't doing, so I had to restart it. All right. Just turn it on and turn it on again. All right. So okay, guys, could you please turn off your microphone, please, if anyone has their mic on. All right, thank you. Okay, so now you notice that we have tested the two extreme points, and they both didn't give us anything worth to consider. However, the only one that did give us the value, a good value, was our maximum point. So indeed, the ultimate revenue, the highest possible revenue, would occur at 40. There are instances where probably when we evaluate the, how do you call it, the endpoints, okay, you would have other values. Okay, so for instance, let's say in this case, we have something like, say, 300, 400, and let's say 320. Well, again, we will choose this one because it gives us the highest possible revenue. However, if a weird instance occurs where probably you evaluate the stream values, let's say we did it at 80, and then 80 ended up giving us something like, let's say, 600, and this is 400, and probably let's say this is 0. I'm just saying, I'm just giving. Then in that case, this actually, yes, it's a maximum point, it's a maximum value, but it is not the absolute maximum. It means that the absolute maximum occurs here. So it's just like saying you have a graph that looks something like this. Okay, something like here, and probably 40 is probably somewhere here, and 80 is somewhere here.
She's suffering.
That's how come.
So she's suffering, and he's doing that.
Okay, so it means that this point here, this is actually the global maximum, and this is a local maximum. That would be the only instance under which the maximum value would not occur here. But however, in our case, the highest revenue occurs at where we found our maximum value. So in that case, we are sure that it does happen. So, okay. All right. So we are going to have applications of the relative maximum and minimum concepts. So let's get into the questions and solve them and see how they happen. Okay. All right, so suppose that the total cost function or the total cost of producing a unit, Q units of a product, where C is this. Okay, so we have this function. This is the total cost function. Okay, now what level of output Q will average cost per unit be minimum? And what is the minimum value? Okay, so again, I remember I told you this. So this is how we're going to apply these concepts one after the other. So how do we first understand the question? It says that at what level of output Q will average cost per unit be minimum? So we want to find the minimum value. The procedure is still the same. Find your function, take the first derivative. When you take the first derivative, equate it to 0, solve for the critical value, okay? And when you solve for the critical value, take the second derivative, test to be sure that indeed that is the minimum value, and boom, you can show. If it is less than 0, it is the maximum. If it is greater than 0, it is a maximum, it is a minimum, okay? So let's get into this. So we have a total cost function here. However, we are looking at average cost. So how do we find average cost? We know that average cost equals total cost divided by quantity. Okay. So average cost is total cost divided by quantity. Okay. So if we have our total cost function as Q squared plus 3Q plus 400, okay, it means you're going to divide all of this here by Q, because all of this is TC. And when you divide TC by Q, you'll get average cost. So you can have something like this. So a way of rewriting this function again, especially those that are carrying the fractions, you can just pull out the fraction 1/4. Then you have Q squared, okay, plus 3Q plus 400, okay? Now, so once you have this, you can divide everything here by the Q, okay? Then it makes life easy for you. So here, if you divide by Q, this Q can cancel one of this because this is squared, and this Q again can cancel this. However, here it still remains like that. So what you're going to have would look something like Q/4, okay, plus 3 plus 400 over Q. So this gives you the, what's it called? This one here will give you the average cost function. Okay, this gives us our average cost function, which we can all see here. Okay, so this is all that we have done here. All right. Okay, so having done this, we can take the derivative of this. So again, if you have to take the derivative of this, well, let's go ahead and try and do it. Now, you have this function here. Let's see how we can take the derivative of this. Now, my friends, we have Q/4. So you can write it as 1/4Q, okay, plus 3. Now remember the last time I taught you something, that if you have something, say 4 over something, okay, here, another way of writing this would be, we can write this 400Q to the power minus 1. Here it has a power positive 1, but when you reverse it, it has a power negative 1. So you can have plus 400Q to the power minus 1. So once you have this, you can easily differentiate this. So let's start. The derivative of 1/4Q is 1/4, because this will, the power 1 will come and multiply this, and 1 minus 1, and it goes away. So you have 1 minus 4, okay? And then this 3 will go away because it's a constant. And when you take the derivative of a constant, it goes away. Perfect. Now, the next one is to take the derivative of this. So here we will now have minus 400, okay? And we will knock down the power by 1. So this is going to be minus 2, okay? So you have a derivative, AC prime of Q is 1 over 4 minus 400Q squared, okay? So we have taken this expression here, okay? And you have this. So again, if you want to rewrite this, write it back into the form in which it was, then you can, so this, how do you call it, 400Q minus 2, you're going to write it as 400 over Q squared, okay? Once you have this done for yourself, okay? So it makes life easy for you once you're able to rewrite this. Okay, so you take this expression here. We can all solve this thing here, where you just have to 1 over 4 again. So we rewrite it in this form, take it to the other side and take the square root of it. And once, you know, when you take the square root of something, negative will become positive, okay? So we take this, in other sense, you can, one beautiful thing is you can do 1 over 4, okay? We had 1 over 4, 400Q minus 2. Another way you can write it 1 over 4 minus 400 over Q squared, which is equal to 0, right? So take this to the other side. And if you take this to the other side, you have 1 over 4 equals 400 over Q squared, okay? So we know, remember this basic thing, cross multiplication, right? This guy will go with this and this guy will go with that, okay? So you can have Q squared equals 4 times 400, okay? And that's 1600, okay? And so you just take the square root of both sides, okay? And when you take the square root of both sides, like this, like killing this guy and killing this guy, knock this guy down by a square root. Or taking the square root of both sides is like saying take the power 1 over 2 of both sides. Okay, so anyway, it just works out for you. So you take the square root of both sides and the square goes away. And the square root of 1600 is what's it called? 40. All right. So we actually, I'm sorry, I am very sorry to have written plus or minus Q. I just want to satisfy the mathematical condition anyway. However, we are looking at quantity and we can have a negative quantity. I hope you understand. So there's no point in even bringing the plus or minus to confuse you, but anyway. So, well, but it's 40, okay? All right. So Q is 40. When you take the square root of 1600, it's 40. So we are saying that at quantity 40, we would have the highest possible, the minimum, what's it called, average cost. However, we don't know if that is true. So we have to do the second derivative test. Okay, we have to do the second derivative test. So let's go and take the second derivative test and the second derivative test, So here we have our function. So please, I can cancel these ones. So we have 1 over 4, okay, minus 400, okay, Q to the power minus 2 equals 0. So let's take the second derivative test, which will be AC prime of Q. So this guy goes away because it's a constant. Now minus 2, okay, minus 2 would come and multiply this, and what do we have? Minus 2 times minus 400 is positive 800. Okay, and then we would knock down the power by 1, so minus 1, so this is minus 3. Okay, and if you have this, this value here is greater than, what's it called? Is greater than 0, okay? And so at this point, we can be sure once it is greater than 0, we can be sure that this is a minimum point. And so at quantity 40, we would make the lowest possible average cost. Now, what is that average cost? We must take Q, which is equal to 40, and substitute it into the average cost function that we found. So what was the average cost function? Let's go back and look. So we found this as the average cost function here. So let's substitute Q into this expression and find our average cost, okay? So we found Q to be 40, and so we substitute it here, and then we had 23. So the least possible cost we would incur given this function is 23. And that is when we are producing at 40, okay? So anything that we will produce above 40, we are going to incur additional cost to produce. All right, so now let's look at this interesting question here. I hope we will all have fun solving it. Oh, sorry, we've already have solved it here. Okay, so I think there's the one I give. Yeah, so there's a homework here for you today. Perfect. All right. Okay, so let's go over this. We'll take time. And this is a past question that I picked up and added it to the slide. So let's just, so oftentimes this is just how your, probably, if anything, your questions probably will look like in some sense. So it says a cable TV company currently has 100,000 subscribers. Okay, 100,000 subscribers. And they pay a monthly rate of 40 cedis. Now, could you please everything? All right, thank you. All right, so great. Now, so they have 100,000 subscribers. Then they pay a monthly something of 40. Now, since a survey reveals that there will be 100. Oh, guys, could you please mute your microphone? Thank you. All right, a survey reveals that there will be 1,000 more subscribers for each 0.25 decrease in the rate. At what rate will maximum revenue be achieved? And how many subscribers will there be at this rate? So we are interested in understanding. Now, if you think about this, let's look at it like DST. Now, if you're paying, let's say 100 and okay, which of these one? Okay, so let's say maybe you want to get the full bouquet for DSTV and you're paying the 365 monthly. So we're saying that every time DSTV reduces maybe their subscription rate, the monthly subscription by a certain amount, 1,000 people more will subscribe for the monthly, the full bouquet or something. That's now. So in that regard, if they don't take time and they are only interested in just reducing, yes, you reduce, you get a lot more people joining onto the train, but you're going to have so many people and you're going to be incurring all sorts of costs and you probably may not be making profits. So we want to be sure that, so what is the price to sell our product so that we can still be making very good profit. So let's understand how we derive this stuff. So please note that we are interested. So let's start from things. So we want to, what will the maximum revenue be and how many subscribers will there be? So we are looking at revenue, and revenue, we know that revenue is price times quantity, okay? So let's get the equation for the price. Let's get the equation for the quantity, okay? So initially, so let's say, let's have P and let's have Q. Okay, so guys, let's look at it like this. So the monthly rate is 40, okay? And then the quantity we have, let's say 100,000 people. So 100,000. So let me use 100K. So this is the initial stuff, the initial information we have. Now it says that. So it says that a survey conducted reveals that 1,000 more people will join whenever they reduce it by 0.25. So the idea is that now we don't know how many times they should reduce, and we don't even know how many people will join the train, how many people should join our train in some sense. So we're going to try and do something here. Let's say, let X be the number of times we reduce the price, so that we, at the end of the day, if we reduce it 10 times, we know we've reduced it 25, maybe 25 CDs or 25 something. Reduce it 5 times, then we'll know how many people. So if we reduce it 5 times, then we know 1,000 times 5 will be 5,000 more people joining in that order. Okay, so we're saying that whenever we reduce the price by 0.25, okay, we will have 1,000 people joining. So every 0.25, 1,000 people will join. Every 0.25, 1,000 people will join. So how many times should we reduce it so that we would have how many people joining? So the number of times to reduce, we don't know. So let's just represent that number of times by X so that we would have X, 1,000 times X number of people joining our wagon. So the idea is that if we reduce it by 5 times, then we are going to have 1,000 times 5 people. That's 5,000 people joining our train. That's the basic idea that we have. So for our number of subscribers, the equation will now be 100,000 plus 10 plus 1,000x. And then for our price, the rate of the product, we have 40 minus 0.25x. So let's put these two together to form one composite total revenue function. So this is our total revenue function. This is how we derive the equation here. So we multiply these two. So you take 40 and the 40 multiplied by 100,000, and you take again the 40 to multiply the 1,000x. And then you do 0.25x times 100k, and then you do 0.25x times 1,000x, and that should give us this. So we put this together, and when you expand it, you would have, I think this is 4 million, right? This here. So this is 4 million plus 15,000x minus 250x squared. Okay. So once we have this expression, we can take the derivative of this and find and apply the concept. Okay. So I'm sure we can all differentiate this, isn't it? So this is going to give you 4 million goes away, it's a constant. And this is going to be 15,000 because it only carries 1x minus, and this will be 500x, okay, equals 0. Okay, so here, this is our first derivative. We take the first derivative here, okay, and we equate it to 0. And once we equate it to 0, we can solve for x. So x here is 30. So x is 30 here. So if we take the second derivative test, we do the second derivative test. The second derivative test would be to do r prime prime of x. And r prime prime of x, this 15,000 goes away, and you're going to have minus 500, which is less than 0. So indeed, because it's less than 0, we know it's a maximum point. Okay, so at that point we'll be experiencing the maximum. Okay, so the relative maximum point, or the point at which we will make the maximum revenue, is when we reduce it 30 times. Okay, so you can just, if you want to find that price, that is just going to be 0.25 times 30. Okay, and that would give us whatever price that would be. So 0.25 times 30, and then subtract it from the 40. That would give you the price. And then we also know that we are going to have 1,000 times 30, and that is going to be 30k. So you're going to have a total of 130,000 subscribers at a certain price, okay? So if we want to evaluate it over a closed interval, then we are going to look at generating the how do you call it, the interval. Now, the point is we can reduce up to 0. Okay, now when is 0, it means there's no reduction. So at this point, the price is 40 cedis. Okay, and when we reduce it 160 times, it means here at this point is for free. Everybody can just go and buy the DSTV dish and whatever, just subscribe. Okay, now you all know how I got this. We got this by doing 40 divided by 0.25. Okay, and that will give you this. Okay, all right. And so in between this, we have found the fact that we can reduce it 30 times. Okay, so we can just substitute these into the expressions and see which one gives us the highest possible revenue. So when we do it, when we substitute 0, when we substitute 0 into the equation, here we have 4 million. When we substitute 30 into the equation, you have 4.225. And then when we substitute 160 into the equation, I'm sure we're also going to have something similar. So in that case, we have found that the highest possible revenue will come from when we reduce it 30 times, okay? And when x equals 30, when you have 4.2225. All right, someone did raise their hand. Who is that? All right, someone, I saw a hand raised. Who was that?
Sir, please, when you get the 160.
Okay, so you remember we said we're trying to give you an analogy here, right? So we says that if we can reduce by 0.25, then 0.25, 0.25. When we reduce 0.25 160 times, okay, we would have 0. So just put 0.25 into 40, okay? Do 40 divided by 0.25 and see what you give me, okay? Is that okay? So when we don't have any reduction, at all, it's 0. When we reduce it, so here the price will be 40. And when we reduce it 160 times, then the price will be 0. Have you checked it? Hello?
Yes, sir. Yes, sir. Yes, please.
Right. Okay, so all right, so I found another one. This was also another past question, very similar to what we have just done. So just take your time. I want you to solve this like as a homework. Let it be something that you can try. And when we meet again next week, it would be what we will start the class with. I want to see how you would also work your way around it. It's very similar to what we've just done. Just take your time and think through it. Okay, so Mensa Michael, you have your hand raised. Yes.
Yes, sir.
Yes.
Sir, please, the question demands we calculate for the rate at which maximum revenue will be attained and the number of subscribers at that rate. But
yes,
we focus on calculating for maximum revenue.
Yes, so I did calculate it. I showed you that you would have 130,000, what's it called? So remember we said we have 40 minus 0.25x, right? And that will give us the price. And then this number of subscribers, which is Q, is going to be 100,000 plus 1,000x, isn't it? So if we found x to be 30, then that is going to be 100,000 plus 1,000 times 30 is 30,000. Okay, so we are going to have 130,000 subscribers. Now, if we have to find the rate, then it's going to be 40, okay, minus 0.25 times 30. Okay, and what is 0.25 times 30? I think that's 7.5, isn't it? So 7.5 minus 40, you have 32.5. I hope it's 32.5. So the rate will be 32.5, and it will give us a subscriber rate of 130,000. Okay. All right, are you satisfied?
Yes, sir.
All right, okay then. Okay, so I saw another hand raised, Bountiful.
Sir,
Yes, please.
when you see when we're multiplying through here, the 0.25, when you multiply it, you get 25,000, not 15,000, right?
Yeah, yes, but you have to expand.
Oh, okay.
So okay, so let's try it. 40 times 100,000 is 4 million. Okay, and then 40 times how do you call it? 1,000x is 40,000x. So plus
Yes,
40,000x. Then 0.25x times 100,000 will be what? So that's 25,000.
yes, sir.
Minus 25,000x. And 0.25x times 1,000x here would be minus 250x squared, right? So group like terms, 40,000x minus 25,000x, that's 15,000x.
Okay. So I understand. Thank you.
Okay, all right. Okay, all right. So my friends, I thank you for your. Okay, no, I think there's one more question. Yeah, let's get through this one. All right. So this is a very simple one that would require you to not think at all. So guys, please, for this one, it's a homework. It follows. It is similar to what we have just done. Okay, so just take your time, right? Do what the demand, what the price is, and what the quantity is, and try and just generate the function and just try and solve it. Now, bear in mind here, we are looking at profit, okay? And you know that profit is total revenue minus total cost. So get which of the functions is for total revenue, what is for total cost, and just, you can easily find the function, okay? All right, but however, if you're also not able to solve it, but I encourage that everyone solves it, or everyone tries it, and then we see what happens. All right, so suppose N is the number of recipients of health benefits, that is. When N is in thousands of elderly people giving us this, okay, so this is the number. And we are supposed to evaluate over this closed interval 0 and 12. At what values of T will the number of elderly receiving benefits start to fall? So we are looking at the interval where we want to test whether it will be falling at a certain interval given this range. So we have this expression here. So you have T cubed over 3 minus 6T squared plus 32T. Okay, so like I always tell you, try and simplify, write things in a way that will make life easy for you. You can have 1 over 3 T cubed minus 6T squared plus 32T, okay? Then in this case, you can easily take the derivative of this, okay? However, even if you don't want to write this, this is quite obvious. If you take the 3 and the 3 comes out here, you're going to have 3, this is going to be squared, then you can just cancel out, okay? All right, so you have T squared minus 12T plus 32. Now, if you have this, I know this is something very familiar to all of us. We call it a quadratic equation, okay? So for my brothers who attended the, how do you call it, normal GSS or GHSs and all the stuff, the teacher will tell you, look for two values that when you add, it will give you minus 12T. And when you multiply, you get 32. Those who went to the international schools will tell you there is a quadratic formula. Okay, and this is the quadratic formula. This here, okay. Please, I hope you remember this, all of you. You said some people call it almighty formula. I don't know what this is. All right, yes. So this is A, and this is B, and this is C. Okay. Yeah. So you just substitute it into this formula, and then you're gonna have what's it called? Two sets of values. Okay. And whatever you get, you just solve for it. It's not a big deal anyway. Either way, whether I went to international school or whatever school, we are all here together. Okay. So, all right. So we substitute this. So 12 and 32, we found factors -4, -8. Now, if you add -4 and -8, you get -12. If you multiply -4 times -8, you're going to get +32. So we just expand it like that. So you have t squared -4t -8t plus 32, and you factorize. Okay, so this is t falls out, and you're going to have t -4, and then here 8 and 32. So 8 comes out, t stays, and 8 goes into 32 4 times. So you still have this. So you're going to have +8 +4. Okay, either way. So we are looking at the interval 8 and 4. Okay, interval 4 and 8, or 8 and 4, either we say the 40 is fine. So we are saying that between 8 and 4, okay, between the interval 8 and 4, chances are that the number of elderly people receiving the benefits will start showing. Okay, and that's all we're trying to say. All right, Ajoyi, I think you raised your hand. Okay, all right. Ajoyi has forgotten his question. All right, guys, so I'll be starting the other class with your other colleagues very moment. So